Okay, and we're back. These next problems are a bit more difficult, a lot of honors problems here. Harry leaves his house and starts to sprint to where Cindy is. If Cindy is 400 meters away and Harry is running out the door at 2 meters per second with an acceleration of 0.2 meters per second squared, how long will it take him to get there? Get to Cindy. Alright, so again, we want to draw this whole thing out. So, what we see is Harry is 400 meters away. So we're just going to draw like that, 400 meters away. He's sprinting out the door, and he has an initial speed of 2 meters per second. And then he's getting faster and faster and faster, trying to get to her as fast as possible. So acceleration of 0.2 meters per second squared. So we want to write down everything we have. We know initial velocity is 2 meters per second. Displacement is 400 meters. Acceleration is equal to 0.2 meters per second squared. And what we're looking for, how long will it take him to get there? So the time. Okay, even though I drew this from left to right, I'm just kind of putting everything into positive because it doesn't say any direction or anything like that. Alright, now that we have our 4 variables, we want to look at our formulas. We want to see which one has all 4 of these. We look at this one, and we see that this one has displacement, this one has v initial, this one has acceleration, and it has time. So we can use this second equation here. So what we're going to do is displacement is equal to initial velocity times t plus 1/2 at squared. Displacement, which is equal to 400, v initial, which is equal to 2, t, which we're looking for, plus 1/2 a 0.2, t again, which we're looking for squared. What you're going to realize with this problem, what makes it an honors problem, is it's impossible to find this without using the quadratic formula. So we're going to have to use the quadratic formula for this, so I'm going to put everything onto the right side. 0 is equal, and then I'm just going to kind of put the one that's squared first over here. So I'm going to simplify this to be 0.1 t squared plus 2t, and since we bring these 400 to the other side, minus 400. Okay, so it's important to know, so the formula for quadratic formula is negative b plus or minus square root of b squared minus 4ac all over 2a. So if you guys remember, the one that has the variable that's squared, this is equal to a. The one that has the single variable, that's b. And the one without a variable is c. Okay, so we're going to plug these numbers in to this point right here. And what we get, negative b, so that's going to be negative 2 plus or minus 2 squared minus 4, let me do it like this, a, which is 0.1, c, which is negative 400. 2a, which is 0.1. Okay. I'm going to speed up doing the math because this isn't a math class, but let's see. When we simplify this, we get negative. And then we get 2 answers for time. We get time is equal to 54.03 seconds. And we also get negative 74.03 seconds. What we should know is time should always be a positive number. So this is going to be our correct answer, 54.03. Okay. But what happens when Harry gets there? Harry calms Cindy down by letting her know that there is only a small dent in the car and the deer is probably fine. But I don't know, the deer doesn't really look that fine to me. Alright, let's look at the next problem. Jim, who was left at the competition, well that's not nice, gets on his bicycle and starts heading home. He coasts due west, so he's going to the left here, at 8 meters per second. At one point he encounters a sandy patch of road that is 7.2 meters across. By the time he leaves the sandy patch, his speed has been reduced to 6.5 meters per second. Assuming the bicycle slows with constant acceleration, what is his acceleration? Alright, so again we want to draw everything out. This sandy patch, 7.2 meters. We know when he first gets on the sandy patch, he has an initial velocity of 8 meters per second going west. And then when he leaves, he gets a little bit slower. The sandy patch slows him down of 6.5 meters per second, again going to the west. And we're looking for what's the acceleration. And we should know, since it's slowing down, acceleration will be going to the right, which is positive. Okay, so let's write down everything we know. We know initial velocity is equal to 8 meters per second. We know final velocity is equal to 6.5 meters per second. We know displacement is equal to 7.2 meters. And what we're looking for, acceleration. However, one thing we have to notice is it says due west, so everything is going to the left here. He's moving to the left, he's going to the left, and everything's to the left. So this is initial velocity is negative, v final is negative, and displacement is negative. Now we're going to look at our formula sheet and we're going to look at which one has all four of these. We notice when we look at this one, this has v final, this has v initial, this has displacement, and it has the acceleration. So we're going to use this formula right here. So we have v final squared is equal to v initial squared plus 2a change in x. Negative 6.5 squared is equal to negative 8 squared plus 2a, which we're looking for, times displacement negative 7.2. Speed up a little bit of the calculations. Get that the acceleration is equal to 1.51 meters per second squared. Again, it's positive because it is going to the right. And as soon as he gets home, Jim realizes he gets a call from Harry letting him know what happened. Jim feels bad and decides to bake some cookies for Cindy, but they do turn out a little bit burnt. Things just aren't going the way they should be for Jim. Alright, let's look at this problem. Another problem that's a bit difficult here. A speeder who is doing 40 miles an hour, or 17.9 meters per second, in a 25 mile an hour zone approaches a parked police car. The instant the speeder passes the police car, the police begin their pursuit. If the speeder maintains a constant velocity and the police car accelerates at a constant acceleration of 4.5 meters per second squared, how long does it take for the police car to catch the speeder? Alright, again, we want to draw this whole thing out. So we're going to draw the speeder. Speeder is going 17.9 meters per second. And then we have passes the police car. We're going to draw the police car in orange here. Police car, is initially at rest. If the speeder maintains and the police car accelerates, a parked police car. So we know his initial velocity is 0. And then, but it's going to be accelerating with the rate of 4.5 meters per second squared. And what we know is, since this police car is getting faster and faster, eventually it's going to catch up with the speeder. So even though this thing is gonna zoom by first, it's gonna eventually catch up and meet up with him. So this is kind of difficult because it looks like we don't have that much information. One thing we do know though is the speeder maintains a constant velocity. What that's saying is, since it maintains a constant velocity, that means the speeder has an acceleration of 0 because his velocity isn't changing at all. So let's just write down everything we know for both of these people. The speeder has a velocity of 17.9 meters per second, has an acceleration of 0. When it comes to the police car has initial velocity of 0, acceleration of 4.5 meters per second squared. And we want to know how long does it take for the police car to reach the speeder. So when they reach right here, what time is it? So this is a little bit complicated because it seems like we only have 2 pieces of information for both of these people, and we need 3 to always figure out the rest. One thing though that's the same for both of these is when the police car meets up with the speeder, they'll have traveled the same amount of distance. So the displacement is the same. So if the police car catches the speeder, that means the displacement of the speeder is equal to the displacement of the police car. Now what we could do then, if we know that, is we could set this equation of the speeder equal to this equation of the police car, since we know this displacement is the same. So what I'm going to do is, for this formula here, I'm just going to put v initial times t plus 1/2 at squared is equal to the displacement of the police car, which is again is also v initial t plus 1/2 at squared. And let's just plug in what we know. We know the initial velocity of the speeder is 17.9 times t, which we're looking for, plus, and we know the acceleration is 0, so this whole thing turns into 0. And for the police car, we know it has an initial velocity of 0, but it does have acceleration of 4.5 t squared. So now we just have to simplify this. One thing that we see is there's t on both sides, so we can get rid of one of the t's. Get rid of this t and this t by dividing both sides by t. And now just do some simple algebra, and then we can find what t is. I'm going to divide this by 17.9, or 79 divided by that, and we get a time of 7.96 seconds. So it's going to take the police car 7.96 seconds to catch up to this speeder. Okay. A bit difficult, might want to look back at that. How far will the 2 cars have traveled by this time? Alright, so now that we know the time of how long it takes the police car, we can use these 3 pieces of information to find how far they traveled. So again, let's kind of write down what we know. For the police car, initial velocity is equal to 0. Acceleration is equal to 4.5 meters per second squared. Time it takes to catch it is 7.96 seconds. And what we're looking for is how far, which is the displacement here. Again, we're going to look at our formula sheet, and we see that this formula here has all 4 of these variables, and we're going to do this problem. Displacement is equal to v initial t plus 1/2 at squared, and we have displacement is equal to 0 plus 1/2 a 4.5 7.96 squared, and we get an answer of 142.5 meters. Okay. Part C, what is the velocity of the police car when it catches the speeder? Again, let's find out all the variables we know. So we're looking for how fast the police car is when it finally catches him. So let's use all our variables. We know initial velocity is 0. We know acceleration is 4.5 meters per second squared. We know time is equal to 7.96 seconds. And we also have displacement, which is equal to 142.5 meters. Now we look at our formula sheet, and there's a few we can use. We can use this one here. We can use this one over here. And why not? Why don't we use this one over here? So we're going to use that formula. V final squared is equal to V initial squared plus 2a change in x. And we're looking for what this final velocity is. Initial velocity is 0 plus 2a 4.5, 142.5. And then what we get for this is final velocity is equal to 35.82 meters per second. Okay, so going by pretty fast when it catches them. Alright, last problem for this acceleration section, conceptual problem. Usually students have a very hard time doing these kind of problems at the beginning. Assume that the brakes in your car create a constant deceleration regardless of how fast you are going. If you double your driving speed, how does this affect the time required to come to a stop? And B, the distance required to come to a stop. Alright, so this is a bit confusing. Let's try to draw this out. So we have a car here, and it's going a certain speed. We're just going to call it V initial, okay? And it's gonna, after a certain amount of time, it's gonna come to a stop, right? And what we also there's it's gonna slam on its brakes, so it's gonna have an acceleration going in the other direction, and we want to know if now this speed is doubled. So let's kind of draw the second scenario out. So we have this car, and now it has double the amount of speed, so it's going twice as fast as the first scenario. So this time it's going to take a little bit longer for it to come to a stop. We don't know how much longer, but it's going to take longer for it to come to a stop. The acceleration is the same though, because it says creates a constant deceleration. So the acceleration is the same, doesn't change even if it's going faster. But we want to know if it's going twice as fast and it slams on the brake now, how much longer is this going to take? What we want to do with these problems is we want to kind of know what variables we're playing with. So we have the initial velocity, we have time, we have acceleration, and we also know that the final velocity is 0 in both of these situations. You want to find the 4 variables that you have playing with, and you want to write them down. So we have V initial, we have time, we have acceleration, and we have V final, which is 0. And we want to look, okay, what formula has all 4 of these? And we see, and we look at this formula here, okay? What we're looking for is this time. How does time change as the velocity changes? So let's just kind of write this formula out. We have acceleration is equal to V final minus V initial over t. Okay? And what we want to do is we want to rearrange this formula so t is going to be what we're primarily looking at. We're looking for time. So I'm going to put t to the other side. So we're going to do t is equal to V final minus V initial over a. We know that the velocity final is going to be 0 for both of these situations. So this is just 0. But what we want to know is when this velocity changes, when it goes twice as fast now, so if this velocity changes by a factor of 2, how is this time going to change? And what we notice is if this velocity changes by a factor of 2, this side is going to get twice as big. So that means if this changes by a factor of 2, the time here also has to change by a factor of 2. So if it's going twice as fast, it's going to take twice as long to stop, for it to stop. So it's going to the time it takes to stop will be doubled. Oh, that's the answer right there. Sorry. Oh, I thought this was the answer. Okay, sorry. So the time it takes to stop will be doubled. That's the correct answer. Part B is we're looking for the distance. So if you're going double your driving speed, how does it affect the distance required to come to a stop? So it says quadrupled, so we have the answer, but let's see how we get there. So again, we're looking at the same thing. We have this car, it's going a certain velocity, and then, but this time instead of time, it's looking for a distance. And we know it's going to slam on its brakes, and then it's going to come to a stop. Again, we know acceleration is going the other way. And we want to look at the second scenario. If it's going twice as fast, so it's going a lot faster this time, and we know it's going to go further, how much further is it going to go to come to a stop? Acceleration. So again, we want to look at the variables we have. We have initial velocity, we have acceleration, we have displacement, and we have velocity final. So let's write it out. Vf, V initial, acceleration, and displacement. Again, what we're looking for is this displacement, and we want to find what this displacement is as this velocity changes. We also know, again, initial velocity is 0. So we look at our formula sheet, and we see, alright, this is the one that has all 4 of these variables. So Vf squared is equal to V initial squared plus 2a change in x. We also know the final velocity is 0. So we want to see how this changes and how that one is affected. So let's try to isolate this displacement. So I'm going to bring V initial to the other side. Negative V initial squared divided by 2a is equal to the displacement. And what we're going to notice is as this velocity changes by a factor of 2, and since it's put to the power of 2, this side here is going to change by a factor of 4. So that means if you change this initial velocity by 2, it's going this displacement is going to be affected 4 times as much. So what happens is it's quadrupled. A little bit confusing. We'll be doing more of these in the future, but this is a little bit confusing. If you want to look through it again, try to look through it again. Alright, thank you guys.